Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll learn about one of the most important decision-making methods for engineers in the practice of noise control.
So let's get started. We've previously defined sounds, but here we'll define noise as being unwanted sound. It's important to recognize that noise for one person is not necessarily noise for another. For instance, the crying sounds of a baby are definitely not noise to a father and mother, whereas for neighbors next door, it might be a nuisance sound. Or the roar of a 5-liter engine could be symphonic to the person owning the vehicle and could be a major hassle and noise concern for neighbors. Noise is important for many reasons far outside of simply engineering applications. Noise causes stress. It increases psychiatric concerns. It reduces and slows down the recovery from illness. It creates challenges in communication. It has effects on unborn and newborns, reduces workplace effectiveness, and many other challenges in society. So as engineers, we are often tasked with controlling noise, specifically by suppressing it in the environment. Examples could include developing laminated glass panes that stop the penetration of urban noise into office and residential buildings. It could be to create quieter combustion cycles and reciprocating engines, or design rotor blades that minimize drone noise. One thing that's important to recognize here is that engineering noise control is often multidisciplinary. It is not simply a mechanical problem or an acoustics problem, but it requires the expertise of many scientists and engineers. Engineering noise control is multidisciplinary. So in the case of the laminated glass panes, this could involve chemistry, materials science, mechanics, in addition to acoustics, of course. Quieter combustion cycles require expertise in heat and mass transfer. Mechanical design of the engine block and so on. Rotor blades require expertise in aerodynamics. And aeroacoustics. Engineering noise control is a multidisciplinary task. Yet, to tackle noise control problems in a variety of applications, we oftentimes are well served by using the source path receiver prioritization of noise control techniques. The source path receiver prioritization tells us that we first should address noise at the source, second, address noise at the path, and third, address the noise at the receiver. This order should be kept strictly to have the most effective solutions for noise control. Let's see an example. Let's consider vehicular noise, such as that noise created by an internal combustion engine. The source is the noise from the engine. The receiver are the occupants in this example. So the source could be the combustion cycle, so thermoacoustics of combustion. Now, we could address this by having more effective fuel burn that reduces cylinder knocking and so on. The path. Well, there are many paths between the engine noise and the vehicular cabin. The engine is mounted, so the mounts would transmit vibration through the frame and into the chassis. The engine also creates directly radiated noise, so you have sound that passes through the firewall and the dashboard. So let's consider that latter path. We could consider putting on an engine block cover. And this helps to suppress some of the noise transfer back through the firewall and into the vehicle cabin. And in the receiving side, we could develop solutions such as perforated seats that are more highly absorptive of sound. Or, in a last resort, we could ask our occupants to wear hearing protection. What is clear through this first example are that noise control remediations closer to the source are often less expensive and more effective. And we'll see that through a few more examples. Source path receiver tells us to prioritize our efforts to stop noise first by addressing the source. In the prior example, it would be to develop a quieter fuel burn. Or if the source noise is tire noise near a highway and then residences across the road, that would be to develop quieter tires. Or in a manufacturing setting, it might be to develop quieter manufacturing equipment. In a household and multifamily dwelling, such as a condo or apartment space, in that sort of application, it might be to have quieter neighbors, kinder neighbors. To address noise at the path, we may develop a cover or enclosure for the loud engine. For instance, if the engine cannot be made more quiet. We might build a barrier between the roadways and residential homes. In the manufacturing setting, if the manufacturing equipment may not be quieter, we might have to put lead vinyl curtains around the factory equipment. Or if our neighbors just won't quiet down, we might need to add or refinish the walls that are facing our neighbors. If we can no longer address the issues at the source or even at the path, we might need to solve this problem at the receiver. In the vehicular environment, it might be active noise control in the vehicle cabin. For the residences near the highways, you might ask your residences just to wear hearing protection and earplugs. For the receiver end at the factory side, you might ask your factory workers to use hearing protection. And then finally, for your neighbors who are quiet and you simply can't address it by enhancing the walls in between you and your neighbors, you might just introduce more sound-absorbing furniture surfaces. These are all examples, and there are infinite possibilities to remediate noise in any given problem. But it is very clear, as noise moves away from the source, it diffuses through all of the phenomena that we've seen before, especially spherical spreading. In addition, in complex assembled equipment, when noise and vibrations propagate, they get into other parts of the equipment, creating new paths for sound radiation when different surfaces begin to vibrate. Remediation approaches at the receiver are costly, challenging to implement, and very often unsatisfactory. So stopping the noise or vibration at the source is preferred. And if we can't address it there, put your attention on the path. Implementing source path receiver methodology will discover that there are many competing interests that can challenge noise control remedies. So take, for instance, one example. The speed to get products to market on schedule could prevent us from developing quieter internal combustion engines. So we might have to balance many interests and stakeholders in the project to achieve adequate noise control at the receiving end. But the fact remains that implementing source path receiver methodology at the earliest part of the design process is the greatest assurance that your remedies will be most effective to stop noise. This is important because the needs for noise control go far beyond consumer satisfaction of products. Noise has many impacts on people's civilization and the earth. It challenges communication, it creates stress, it delays recovery from illness. It degrades the integrity of structures, including structure-borne noise or vibration. It reduces efficiency of operation, and noise is also a common sign of failure. Noise reduces biodiversity and suppresses the diversity of species in our environment. It disrupts means to detect predators and inhibits mating habits for many creatures. As engineers, we are challenged with creating solutions for people in their world. By acquiring the skills here in this course to analyze and shape acoustic fields around us, we are challenged to apply this knowledge by upholding our responsibility as engineers to create solutions for people in their world. Let's summarize what we've learned. The only way to address a noise problem with minimal time, minimal expense, and minimal stress is to approach the problem with a source, path, receiver solution priority. This is instrumental to success in noise control. Noise compromises many aspects of the quality of life, the pursuit of technology, and the sustainability of civilization. We as engineers must use our knowledge for the good of society. In fact, this is an integral part of the professional or PE engineer's creed.
That's it for this video. Now that we have a foundational understanding of acoustic waves and acoustic wave characterization, in upcoming course videos we'll learn about how multiple acoustic sources combine together and are analyzed, as well as learn how waves propagate through materials and multiple layers of fluid.